so these are, this is day 2 for Unit 2. We are going to talk about atomic theory. Last class, you should have gone over the periodic table. You kind of learned how elements were grouped together based on similar properties. You learned about kind of like where things are on the periodic table, metals, nonmetals, etc. So today we're going to talk about atomic theory. So the first thing we are going to discuss is the difference between a law and a theory. Because in science, we have both laws and theories, and they mean different things. So a law, that is describing what happens. So it's basically the observation, what is going to happen. There are lots of laws in physics. Okay, so this is just describing what is happening. Whereas a theory, that is the how or the why it happens. So that's going to be the reasoning behind it. So atomic theory, like what we're going to talk about today, these are all theories like how or why, this reasoning to explain an atom. Okay, and theories can be changed and improved as repeated scientific data and observation conflict with the current theory. So as scientists get more data, they can change their theory. Okay, the best one that I have, like the best thing I can think of is, so we all lived through COVID, right? And at the beginning of COVID, these scientists had these ideas and theories about how COVID was spreading, how we could prevent it, right? But as like they continued to study it more, what they thought was true at the beginning turned out to be like not quite as true. Some things were different. And so their theory surrounding COVID, its spread, changed based on the data that they collected as they watched it spread, and what worked to help combat the spread and what didn't. So theories are able to be changed based on the data that's collected and examined. Laws do not change. Laws are really just the observation of what is happening. So it isn't going to change. All right, so we're going to talk about atomic theory today. So that's theory about the atom. Well, an atom, that is the smallest particle that exhibits properties of that element. So you cannot get to a particle smaller than an atom and have it exhibit the properties of the element it's supposed to represent. So a hydrogen atom is going to represent particles of that atom. But the things that make up atoms, like protons, neutrons, electrons, those do not have properties of that element itself. Okay? The first person to propose the idea of an atom was Democritus. So he was the first person to propose the idea of an atom. And he didn't really do anything else with it. He was like, yo, I think an atom is a thing, and left it at that. The first scientists to really talk about atoms and come up with their own theory, this was John Dalton. So Dalton came up with what we refer to as the billiard ball theory. And that's because his model here looks like a billiard ball. It just looks like a sphere. There's nothing special about it. He said it was just this one dense sphere. Looks like a billiard ball, nothing special about it. So along with this model that he came up with, there are 4 specific points that go along with his theory. The first one is that atoms are indivisible. So there's indivisible atoms, meaning it can't be broken up into smaller parts. His second point is that all atoms of the same element are identical. Meaning every single atom of hydrogen is going to be the exact same. Every single atom of boron is going to be the exact same. His third point is that atoms of different elements are different. Such a concept. No one would have thought of that before. So atoms of different elements are different. So an atom of hydrogen is not the same. It's going to be different than an atom of boron or helium. Lastly, atoms combine in whole number ratios to form compounds. And the big point of this is that you're not going to have half of an atom in a compound. So you're not going to have like H1.50. They're always going to be whole numbers, like H2O, H2O2, CO2. Okay, we're not going to have half of an atom in there. They're all going to be whole numbers. Okay, so this is all what Dalton thought to be true. He thought each of these 4 points were true about an atom. Okay? But then came along this guy called J.J. Thomson. Thomson came up with what we call the plum pudding model. And that's because his model looks like the British dessert called plum pudding. He was a British dude. Okay? If you were curious, plum pudding looks similar to like a blueberry muffin. Okay? But, so it's this idea that there's the existence of negative electrons in a positive atom. So you're going to see this a lot. This here, the lowercase e with a negative like as the exponent, that is shorthand for electron. You're going to see that a lot. That's not just me who uses that. That is like the universal shorthand for electron. You will see that frequently. So he discovered the existence of negative electrons in a positive atom. So he thought that this atom here, it's positive, but we've got these negative electrons just floating around in there. So it kind of looks like a blueberry muffin, plum pudding, these electrons just hanging out inside. Okay, and to do this, he used a cathode ray tube. If you are curious what a cathode ray tube is, I'll link a video on Canvas for you to go and watch it. But I don't really care that you know what it does. You just have to know that Thomson used a cathode ray tube. You don't have to know specifics about it. Just got to know cathode ray tube, that goes to Thomson. Because you do have to know all of these dudes, their theories, what they thought, their models. You got to know that. Okay. Next is Ernest Rutherford. All right, next we got Ernest Rutherford. And he used the gold foil experiment. This is credited to Rutherford. And this gold foil experiment, what he did is he took positive alpha particles and shot them at gold foil. These positive alpha particles were shot at a piece of gold foil. And this here, this first picture, this shows what happened. So we had these alpha particles shooting at gold foil. Almost all of them, so most of them, shot straight through in a straight line through the gold foil to hit like his little shield at the back. Okay? However, some of them managed to, seems like it hit something in the gold foil and shot off in different directions. So while most of them continued in a straight line straight through the foil, some of them seem to hit something and get deflected. So this led to Rutherford's conclusion that there is a small positive nucleus in the atom. And these alpha particles hit the nucleus and were deflected. So that's this. So according to Thomson, right? Thomson had that plum pudding model. These electrons, it was a positive atom, and these electrons were just kind of randomly distributed, mostly empty space. So, and since electrons are so small, these alpha particles should have just shot straight through, not been deflected. However, Rutherford discovered that there's a nucleus in the center because some of these alpha particles did get deflected. So they hit something large enough to interrupt their path, whereas the electrons would be small enough to not disrupt. So he discovered that there's a small positive nucleus and confirmed that the atom is mostly empty space. And this was the new model, Rutherford's model. You've got your positive nucleus in the middle, and then these electrons are just kind of spread throughout the atom. Next, we have Bohr. And Bohr is the model that y'all are going to be most familiar with because this is the model that you're taught in middle school. Okay, so Bohr came up with the planetary model. Okay, and it's called the planetary model because if you look at it, it literally looks like a model of our solar system, essentially. You have the nucleus in the center, which could kind of look like the sun, and then the electrons are on these like orbital paths going around that nucleus. So Bohr said that these electrons are arranged in energy levels. So each of these paths being a different level. And they specifically, these electrons specifically orbit the nucleus like planets. So we still use Bohr's model today. It is really helpful in talking about how electrons are on specific energy levels, looking at it in a 2D space. It's really easy to draw, okay? However, Bohr is not the most up-to-date model. The most up-to-date model is done by Schrödinger. So Erwin Schrödinger, he came up with what's called the quantum mechanical model. If it sounds physicsy, it's because Schrödinger is a physicist. So the name might sound familiar if you're familiar with with Schrödinger's cat. If you're not, I would recommend you kind of look it up. It's kind of cool. It's this idea that he put a cat in a box, closed the box, and walked away. Whenever he comes back, the cat is considered both alive and dead, because he has that cat is not being observed by anyone. So it's this idea that the cat can be both alive and dead because no one is able to observe the cat as alive or dead. It's one of the two, but he doesn't know which. So it could be it's either, it's both. You don't really need to know that. That has no bearing on physics, has lots of bearing on physics, but not on chemistry. I just think it's kind of cool. But it's the same dude. So he's a really popular physicist. So, but the quantum mechanical model, what Schrödinger discovered is that these electrons are in clouded orbital regions slash levels. Now this is a distinction from Bohr's model. Bohr said that these electrons have essentially orbital paths going around the nucleus, or they orbit the nucleus, okay? That is different than Schrödinger's idea of orbital regions or orbital levels. So a path goes with Bohr, or an orbit goes with Bohr, whereas an orbital region or an orbital level, that's Schrödinger. So you really need to make sure that you know the difference between those, because if on like your assessment or your progress check, it talks about an orbit or a path, that's going to be Bohr. But if it says an orbital region, that's Schrödinger. Even both of them have like orbit in it. Okay? All right. So, he said that they're in these clouded regions, okay? However, there's no way to know the exact location of an electron at any given time. You can only know the probability of where you can find an electron at any given time. So Schrödinger is big on probability, okay? So basically what he's saying is there's this region where the electron is hanging out, okay? You can only know the probability that you're going to find it in this exact spot in this region. You cannot know for certain where this electron is located at any point. And we're going to talk more about this next unit. We actually go like deep into the quantum mechanical model and talk about things like electron configuration that have to do with Schrödinger's model. All you need to know for this unit is that this is Schrödinger's model. It's called the quantum mechanical model. It is the most up-to-date model that we use. Okay. The last scientist we're going to talk about is James Chadwick. Chadwick discovered neutrons. Okay. I remember that James Chadwick discovered neutrons. If you didn't know, Jimmy is a nickname for James. James Chadwick is actually Jimmy Neutron. So if you're not familiar, Jimmy Neutron was a show on Nickelodeon that was out when I was growing up. So like 20 years ago. Like 15 to 20 years ago, Jimmy Neutron was on Nickelodeon, okay? It was a big show, like huge kind of Nick show about this boy genius. His name was Jimmy Neutron. The creator of Jimmy Neutron named his character after James Chadwick. So James Chadwick is literally the real life Jimmy Neutron. So Jimmy Neutron, like this is, he was actually named after him. So that's how I remember that Chadwick discovered neutrons. Because you do, like I said before, you do have to know the dude of what they discovered, their model. Okay. Now, Chadwick discovered neutrons, and along with his discovery came about essentially two statements that are like that he came up with and one new discovery of a thing. So he figured out that the mass of an atom is not always the same. So what he means by that is just because an atom of hydrogen, or no, I'm going to go with helium. An atom of helium has a mass of 4. That doesn't mean all atoms of helium are going to have a mass of 4. Some of them can have a mass of 4, 3, 5, okay? They can have different masses. That atom can also lose or gain mass as well, okay? Now, he also discovered that these neutrons are neutral, so neutral neutrons are found in the nucleus. Neutrons found in nucleus. Along with this discovery that the mass of an atom is not always the same, came along with the discovery of what we call isotopes. So an isotope is an element with the same number of protons but different number of, oh sorry, why did I write electrons? It's a different number of neutrons. Sorry about that. Different number of neutrons. So an isotope has the same number of protons, but a different number of neutrons. So carbon is a really common one. So carbon's average atomic mass is 12. That's what most carbon atoms, like that's the mass of most carbon atoms. Some carbon atoms, though, have a mass of 14. So if you've heard of carbon-14, that's an isotope of carbon. We've got carbon-12, carbon-14. Those are different masses of the same element. Okay, so we went through all of these scientists, and if you noticed, as some of these scientists discovered things, it canceled out some things that other scientists had discovered previously. So we're actually going to go all the way back to Dalton. And we're going to determine which parts of these theories are still true to this day and which ones aren't. So Dalton came up with 4 points. Okay? So, indivisible atoms. That's what he said. Is this still true today? Are atoms indivisible? Are they made up of smaller parts? So they are made up of smaller parts. So is this true, indivisible atoms? No, this is not true. So what he meant by indivisible atoms is that there are no smaller parts that make up an atom. However, we know that atoms are made up of protons, neutrons, electrons. So this is not true. Atoms can be divisible into smaller parts. Okay? Are all atoms of this, so all atoms of the same element are identical. Is this true or not true? Not true, because what did we just learn about? Isotopes. Yeah, so isotopes, discovery of isotopes makes this not true. Atoms can be the same element, but have a different number of neutrons, have a different mass. Okay. Atoms of different elements are different. True or not true? True. Yep, this one's still true. That's what makes different elements. There has to be something different from one atom to the next. And then atoms combine in whole number ratios to form compounds. True or not true? True. Yep. We are not going to have H1.50. That does not exist. Okay. Next is Thomson. And he said that that there are negative electrons in a positive atom. Is this true or not true? True, not true? Y'all saying true? Sorry, no, it's not true. So, it is not true because an atom is not positive. Atoms are neutral. So atoms are made up of negative parts and positive parts. But in order for it to be an atom, those negative and positives have to cancel each other out. We have to have the same amount of each. If we have a charged atom, it is no longer an atom. It's called something different. It's called an ion. atoms themselves are neutral. So, yes, there are negative electrons. That is so true. But the atom itself is not positive. It's neutral. Okay. Next is Rutherford. And Rutherford said that there is a small positive nucleus in an atom. True or not true? True, yes. So this is where that positive part comes in. It's the nucleus is positive because that's where the protons are. Okay? And an atom is made up mostly of empty space. True, not true? True. All right. All right. Next, Bohr said that electrons are arranged in energy levels. Is this true? Yes. Energy levels is true. Do the electrons orbit the nucleus like planets? Yeah, so this is not true. So they are arranged in energy levels, but these energy levels are not like orbits around the sun. So the electrons do not orbit our nucleus, but they are arranged in energy levels. These energy levels just don't look like these paths, these straight paths, essentially. All right. Schrödinger. He said that the electrons are in clouded orbital regions or levels. True or not true? True. So they're not in these orbits. They are not in these paths. They are in these regions. So they don't follow nice paths around the nucleus. They can be found anywhere within these clouded regions that are determined by their energy level. Last one. So Chadwick said that the mass of an atom is not always the same. True or not true? True. He also said that neutral neutrons are found in the nucleus. True or not true? True. All right, so the next thing, I'll leave it just a second. The next thing is talking about properties of protons, neutrons, and electrons. So those of y'all in class, y'all have a card sort, and y'all are going to sort those based on, so you've got properties of protons, neutrons, and electrons. You're going to sort them based on who they belong to. Those of y'all watching at home, I will throw the key up on here so that you can copy it in just a moment. All right, so this is the key. So this is proton, neutron, electron. So in a proton, these protons are found in the nucleus. They're the same size as the neutrons. They have a positive charge. If we change the number of protons, we're changing the element. The symbol for a proton is a lowercase p and a positive in the exponent spot. And then in a neutral atom, we're going to have the same number of protons as electrons. Neutrons, they're also found in the nucleus, and they're going to be the same size as a proton. They have a neutral charge. If we change the number of neutrons, we're making a different isotope. The symbol for a neutron is a lowercase n and then like a 0 in the exponent spot. And in a neutral atom, the number of neutrons is usually very similar to the number of protons, but it's not always. Last, for electrons, these are found in the cloud. They're very small. They have a negative charge. If we're changing the number of electrons, we're creating an ion. The symbol for the electron is a lowercase e with that negative. And then in a neutral atom, we're going to have the same number as the protons. Okay, so I'm going to pause this video if you need to copy it down. But if you have questions, please come see one of us in tutorials. Otherwise, I hope y'all have a great day.